All right, so now I want to talk about this one, Linux buffer overflow with listening shell, because what we did before was a relatively weak attack where we took the code and we did not add any new code to run. All we did was redirect with an address to a different part of the code that the developer wrote. Now, this turns out actually to be a very valuable technique called return-oriented programming, where you don't inject any code, you just inject addresses and use code that's already there. It turns out to be extremely useful to bypass address space layout randomization and data execution prevention, which are the main defenses that are implemented by all modern operating systems. Address space layout randomization means every time you load the program, it randomly relocates in memory, so you can't find addresses to jump to. And data execution prevention means that if you inject something into a data segment, like a password, it won't execute. That area is read, write, but not execute. And so to avoid those, you do in fact reuse code that's already there. And the way you find code is, even in the latest versions of Windows, there are some segments that are not in fact relocated randomly in memory. So there is some code sitting around you can use. But anyway, that's why this technique, which does seem very limited, I didn't get to add any new code, turns out to be the one that survives most modern defenses. And we've learned how to use that to take over machines. But we're now going to go back and actually inject code and run it. And that's what we didn't do before. So that's what this is. We're going to inject shellcode that listens on a network port, which is what you typically want to do. So I've already got this set up. Address space layout randomization is already turned off. We did it before. And so you download and run this vulnerable program. And I'm just going to pick up in my Linux machine here. All right, so here we are. I want 203. All right. And so the program, let me just clear, is ed3a. All right, and it tells you have to implement it with a string. You have a command line string. So let's look at the code. All right, so what this does is, here's the main routine. Here's the argument, the usage message that pops out if you don't have a second argument. And if it does have a second argument, then it prints the location of the ESP, just so you can have a number to see if address space layout randomization is on. Then it calls copier, and then it's done. And all copier does is do a string copy of the string you put in the command line argument into a buffer that's 1,000 characters long, and then return. And all it does is it returns this I, so which is the ESP in here, just so you can see where you are. So the ESP is not important. The only thing that's important is this one line here, where you do a string copy of a string in the command line into a buffer that is only 1,000 characters big. That means, of course, if we put in more than 1,000 characters, we have a buffer overflow, and that's what we're going to exploit. So the first thing we're going to do is fuzz it. Now I've made a fuzzer here, a very simple fuzzer. This fuzzer just inputs a number from the command line when you input, and then it prints that many A's. So if you do fuzzer 10, it prints 10 A's. If you do fuzzer 100, you get 100 A's. So that's pretty simple. It's just a way to test this program. So now we can test it for long links. So we /ed3a, and here, if you want to run a command and put the output here, you can use this dollars parentheses syntax. You can also use backtick, but the dollars parentheses I find more easy to use in other environments, so I've gotten used to it. So run the fuzzer on, say, 1,000. And it's ed3a. All right, so it finished without crashing. So let's try 2,000. And we get a segmentation fault. So that's what we expect. 1,000 fits in the variable. 2,000 is enough to make it crash. And in fact, 1020 is enough to make it crash. Let's just do that. As you might imagine, you don't really need to go much past 1,000 before you hit something important. 1020 is enough. So now we can use the debugger on that program, and we can run it with that same parameter. And notice what happens. It's telling you here it crashed with AAAA in the instruction pointer. And you can see that if you go in info registers, the EBP is full of A's, and so is EDX and EBX. But the important thing for us is EIP is full of A's. This means we got the simplest, most exploitable buffer overflow, where some of those A's we injected ended up in the instruction pointer, controlling the operation of the code. That's the easiest one to exploit. So now we have to locate the EIP. So we're going to make this one instead. This is going to be EX1 for the first version of an exploit. So I'll get out of here and nano EX1. Put in that code and get rid of its escape Y. Yeah, good. And now, so what this does is it prints 1,000 and then it prints B, C, D, E, F, the 20 characters are like that. That's all. So now we can tell which characters ended up in the EIP. So I save this. And I am going to execute this one. Plus X, EX1. Now this can be executed with EX1. There you go. It's printing 1,000 A's and then B, C, D, E, F. So now I can go back into the debugger. And I can run, taking output from the fuzzer, or not fuzzer, but from that thing, EX1. There, this thing will print that 1,020 characters and feed it into the program. And now it crashes with 45, 45, 45, 45. So that's A, B, C, D, E. The E's here are what ended up in the instruction pointer. So now I've found how to control the instruction pointer. Now all I have to do is get some code to run. And the easiest way to do that is to use Metasploit. Metasploit is a powerful hacking tool. Probably used it. There's a Linux version. You can just download it from there and install it. And when you do, you get a variety of useful tools. And the one we want is MSF Venom. You can find useful MSF Venom tools here. I put it in sudo, which is necessary if you're using a Google Cloud Linux machine, but not if you're using this kind of machine. Doesn't matter whether you do it or not. But this is MSF Venom, list payloads. And then I only want payloads that are for Linux, and I only want ones that bind TCP to make a shorter list, because there's something like 200 payloads. So it can be a chore to hunt through them and find the one you want. All right. And it lists a few of them. And the one I want is this one here, x86 shell bind TCP. And there it is. That's the name of the one I want. This is the simplest one. Shell bind TCP. The one that is not staged. This one. This one is all in one code. It doesn't have to have two. The staged one is more annoying. It has to run and then download more code. This is the simplest one. This will just start listening on a port. This, by the way, is not a very powerful attack. If you were to do this to a real server, you would open another port like port 4444, which is the default, and start listening. And as we mentioned in the Splunk part of this, if you have proper network traffic controls, you will not allow people to send traffic on a port that you're not using to your server. So starting a listening shell on some goofy port will not work unless your server actually doesn't have a firewall, which is very unusual these days. But anyway, that's the one we're going to use here just to make it easy. And so to see how it works, you do -P for that payload, and then you can list the options to see what options you have to specify to use this. And takes a little while. Okay, there we are. Let me see if I can roll up, not that way, this way maybe. All right, good. All right. So there you have it, binds TCP inline. And there's who wrote it. And here's the basic options. The listen port is by default 4444. And you could specify the target address, but you don't have to. And all the other parameters are optional. So in this case, you don't need to specify anything if you're content to just listen on port 4444 and have the defaults for these details of how it works, which is all we need for what we're doing here. Although it looks like in this case, I am going to choose a custom port in my instructions. Doesn't really matter. All right. So here we go. Come on, come on. There we are. Right. So this is going to make the port 31337. All right. That's what I chose here. Doesn't really matter. It's going to put the output in Python. This is why Metasploit is so wonderful. It's going to write the assembly code. It's going to write the raw binary, and it's going to put Python code that will put it there, just like the poke that someone was talking about in the chat. So get out of this with Control C. All right. Shift Control V. Okay. This is what's going to do it. It's going to use the shell, the payload we chose with port 31337, and the format is Python. And there it is. That is the Python code that defines a Python variable that includes the assembly code we need. Now, notice here, it might have a null byte. Mind it, it's different every time you make it, but it often has a null byte, and there it is. If you have a null byte in your string, that's no good because C terminates strings with null bytes. So if I try to inject this somewhere in that 1,000 characters, it's going to terminate the string early, not cause the buffer overflow, and nothing's going to work. So I can't just use this kind of raw payload. What I have to do is use some more of these options. And what I'm going to do is I'm going to use the alpha mixed version, which will only use letters and numbers, no unprintable characters, which is, of course, makes the shellcode bigger, but it is safe. If you're injecting into a string, that's one easy way to avoid using any goofy characters. You could also just dodge the null bytes, but while you're at it, you probably have to dodge spaces and tabs and such too. And so if you have enough room, and I know I have 1,000 bytes to play with, then you don't need to mess around. You can just use only printable characters, and then it's going to be easier. So there's MSFN, that's the command I need. They'll be on that port and do the alpha mixed, and this appendix equals true. I don't really quite understand what it does, but I found the exploit works better if you turn on that optional option. All right, so that's going to give me shellcode that doesn't have any nasty characters that will break the string. There we are. And now it's much bigger, 1137 bytes. But that's 1137 bytes of Python. The actual binary is only 232 bytes. So it'll fit in my 1,000 bytes I have to play with. Besides, I might be able to go beyond that 1,000. I can just keep overflowing until I hit a memory region limit. Now, I'm going to need this copied into the clipboard. All right. All right. And now I've got a, okay, here we go. Copy that thing into the clipboard. And now I'm going to make EX2. Okay. So a nano EX2. All right. And first I'm going to put in what's in the clipboard now. All right. And now I've got stuff to go before that, which is here. User bin Python is the only thing that goes before that is the shebang line. Okay. It has to be the first line. Okay. Then I define the buff. And now below the buff lines, I put this stuff. All right. Now this is an op sled. 90 is the byte for a command that does nothing, nop. And we're going to have 500 of those. Then we're going to have enough A's to fill in the gap between a NOP sled and the buffer. So what's going to happen here is it's going to have the attack is going to consist of NOP sled, then the buffer, which is the exploit code I'm going to run, then the suffix, which is going to be enough A's to make the total length 1012, and then the EIP. And I do not know what address to put in the EIP yet, so I'm just putting in 1234, just so I can spot it. This is how you construct a dummy payload. The NOP sled is there to make my exploit more reliable. And you'll see in a minute why it's good to do it that way. So I save this. And this is EX2. So, yep, chmod it and run it. Good, that's what I figured. Chmod plus X, EX2, and run it. All right, this is the NOP sled. This random junk here is the payload that came from Metasploit that will actually open a listening shell. Here's a bunch of A's just to pad it. And there's the 1234 that I want to put in the EIP. And what I want to do is I want to make this jump back into the NOP sled, and then it will do NOP, 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 and run the egg, which is my payload. And that's why I put in the 500 bytes of NOP sled. It gives me more reliability. If some of my assumptions are wrong on the target server, the address layout might be different than on my test server. So instead of jumping directly to the start of the payload, I jump into the NOP sled. And now if I turn out to be wrong by 100 or 200 bytes, it won't matter. The exploit will still work. That's why people use NOP sleds, just to make your payload more resilient. All right, and so now I'm going to use, see what's going on here. Right, we're going to find the NOP sled in RAM. Right, I'm trying to figure out where to put the breakpoint. Okay, so first I run this thing in GDB, -Q, and this thing is called ED3A. Okay, now I'm in. Now I'm going to disassemble copier. Copier is the function that copies the thing. And you can see right here is the string copy command that copies the argument that came from the command line when you invoke this program and puts it in the buffer that's only 1,000 long. So this is the point where the buffer overflow happens. And return is where it will try to return to the stored return value, which I may have corrupted. So I want to break after that call command, but before the return, if I want to examine memory after the buffer overflow. So I can just choose the command after the call. And in my machine, it is here. So I'm going to copy that address and break there. And when you put an address in, you have to use a star. There. So now it'll break at that point. Now I can run and use the output of that EX2, which includes my dummy payload. So it goes, it hits the breakpoint. Now I do info registers. And I see the ESP is CAF0 and EBP is CEF8. So that's the range I need. Let me scroll down in my instructions here. Okay. Yep. There's so. Okay. So I have to remember this. CEF8 is where the stack frame ends. So I examine 410X might do it. We'll see at ESP. I'm going to look for CEF8. And I have to press return to get more because it didn't all fit on one page. CEF8, I think. Let's go up and see. Right. It was CEF8 is the end of the stack frame. So that is here, CEF8. And you see it worked. These are the A's. There's the 1, 2, 3, 4. It's going to be in the EIP. So it's working. The 1, 2, 3, 4 is targeting the EIP. Now I just need to choose an address. And the address to hit it would be somewhere in this NOP sled here. It doesn't really matter where, somewhere sort of in the middle. but you do need an address that doesn't have any null bytes in it. So you wouldn't want to use this one, or it would break your string. So I'll just take this one. There's the address to inject. All right, and there's nothing more I need to do in the debugger here, except it might be fun to run it and verify that 1, 2, 3, 4 ends up in the instruction pointer. So I'll have Q to quit doing this, and then continue. And it does end with 1, 2, 3, 4 in the instruction pointer. These are ASCII 1, 2, 3, 4. In ASCII, 31 is 1. In hex, 31 is hex for 1, 32 for 2, and so on. So that's working. So I'm going to quit the debugger, and I'm going to copy my EX2 to EX3. I always save them and make another version because you often make mistakes and you have to go back and pick up where you left off. And so here, that the EIP, I'm just going to put in a comment, the thing I copied from the debugger. There, that's the address I want. It's useful to do that because you can make a mistake here pretty easily. Okay, \x, you have to put the bytes in backwards, 60, \x, let's get rid of the colors, \xcc, \xff. Okay, if I've done it right, it's FFFFCC60. All right, that will jump into the NOP sled, and then it'll run my egg. So this attack should work. All right, and let me scroll down in my instructions and make sure I haven't forgotten anything. We complete the exploit code. Yep. And now we can just run it directly. We could do it in the debugger, but I guess I'll do it this way. All right, could do it directly, but we'll do it in the debugger first. GDB -Q ED3A, run, taking the output of EX3. All right. The program runs, and it never returns a prompt. It's just running. So it's now running the payload, listening. And so I just have to leave this terminal running, I think, and let's have a new terminal, which should be, is it terminal? Maybe it's file. File, open tab. All right, we'll have a new tab. And now I can do netstat -pant, for example. And this will show there is a listening process on 31337. So my program that was just supposed to copy something in return is now running the egg, and the egg is listening, and I can connect. Let's see if I have netcat. I do, good. Then I don't need to install it, so I can just use netcat on a local host on port 337 or 31337. And now I can do who am I? Your Debian, and I can do ls. So I have a shell. I'm not getting the prompt, but I can execute commands and see the response. This is a remote shell, and I could connect from another machine to this IP address now. That's the point. So this is some of the missing steps to make a real exploit, a remote code execution exploit that takes a program that does something completely different, like process a video file or an image and make a listening shell so you can now connect remotely over the network. That's what I wanted to show you. And there are some challenges here to find some flags. So I'll stop this one.